So we're now at the back half of 8.1, and I'm at the bottom of page 525 where it says let's solve applied problems. Some information in here, but I'd like you to pay attention that it says pay attention to the known measures. If we have information, and we will, that is given, we will keep going back to what is given. We'll have to use our calculations, but there's a chance that we can mess up on the calculations and then get the rest of the problem wrong. So as most as we can, we are going to keep going back to the known measures. And then they put a little note at the bottom that when we're looking at sides, we're probably going to round them to 2 decimal places, and angles are probably going to be rounded to 1. I will put information in the test, and you will have information in the homework, but a good rule is that we'll do sides to 2 decimal places, and we'll do angles to 1 decimal place. So right now you're looking with me at the top of 526, and we're going to do some of these calculations. I went ahead and rewrote at the top, make sure our calculator is in degrees, because it's not funny when we do the whole calculation and we had everything in radians. A couple of examples, and these are really nice and simple. Looking at example 6, there's a whole lot of information going on, blah, 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 blah. We need to pick some data out, but we already have a drawing. And then what is the width of the river rounded to the nearest meter? Well, here is our river. And looking at our river, they had given us information like this is the distance we walk. It's a side. This is the angle. It's going to mention in here that the angle measured and formed from where we are and where we want to go is 20 degrees. And then we're looking for a side over here. And you need to run through SOHCAHTOA in your brain, the ratios in your brain, however you want to see them. But when you have an angle and you have the opposite side and you have the adjacent side, it is screaming for us to set up tangent. So tangent of our given 20 is opposite over adjacent. Opposite's B, adjacent's 200, and then you're going to use your algebra to solve. I'm going to multiply both sides by 200, which is what I have written here, and then it's approximately this number, but then going back to the directions, the nearest meter, right here, 73 meters. We're done. It's about 73 meters across the river. Another one very similar, finding the inclination of a mountain trail. You've got a lot of blah, blah, blah about the picture and stuff and the hotel and scenic overlook and elevation and length and all of this good information. And so we need to piece some parts together, but what their bottom line of what they're asking is, what is the inclination or the grade? In other words, what is this angle of the trail? And so to do that, we're going to need a couple of pieces, either given or maybe we have to adjust it for a little bit. But it says the actual trail is 14,100 feet. So the question being, what is the inclination? Then I need something over here. Well, looks like they already did the work for us, that if we go up to 11,100, when we started at 8,000, then they already are telling us that that difference is 3,100. So if we have an angle, we have the opposite side, and we have the hypotenuse, we know that very well as sine. And they already have it set up for us. Sine of what I don't know is my opposite 3,100 over my 14,100. And so I'm going to type this in my calculator, and then I need to do something with it. And they have rewritten it nicely that what we're really looking for is the angle B, and that means we've got to do the inverse sine of this. So I'm going to type in 3,100 divided by 14,100. I'll hit equals. I'll do inverse sine, and it's showing up about 12.7. They didn't tell us where to round to, so we're going to leave it at 12 7/10 degrees. We're moving on to a concept. Again, remember, you can stop this video, and you need to. You need to stop it, think, pause, write down notes, write down some notes for yourself, use sticky notes. These will be problems like what you will see on the homework, and you need to fully understand them before moving on. So I would hit stop, and then come back right here, and we notice, or we see, it's talking about vertical heights. Vertical can sometimes be measured with what's called an angle of elevation or an angle of depression. And if you look at the top of page 527, you're going to see a couple of these examples, or both of these examples. So if you look at your eyeball, and if you had a horizontal line from your eyeball, then the angle going up to what you're viewing, looks like a UFO there, the angle to what you're viewing, or maybe it's a hat that just flew off, that angle is the angle of your elevation. If you're in class, I'd be flapping my arms all over the place trying to show you from one arm to the other's elevation. And then here, if we put the horizontal line again at your eyeballs, but this time you're looking down at the UFO fell, I don't know. And so looking here, this is the angle of depression. From there, you've got right triangles, and you guessed it, we can use SOHCAHTOA. So we'll look at this example here, which is example 8 on page 527, finding the height of a cloud. Meteorologists find the height of a cloud using a device called, and I'll call it a ceilometer. If it's German, it would be a ceilometer, so somebody pick a word for me. And it consists of a light projector, vertical light, and detecting and scans. And then we're at Midway Airport in Chicago. It's where it was first, or it was employed, not first, to find the height of a cloud cover. So it was set up 300 feet from its light projector. And so we have the light projector and the light detector, and they're 300 feet apart. If the angle of elevation, and if these were my eyeballs on this detector, my elevation angle would be 75 degrees. And so what's the height of the cloud cover? From my angle, I have adjacent, and I'm looking for opposite. We know that as our friend tangent. And with it being tangent, I set it up as opposite over adjacent, which is the given 300. I'm going to do that algebra again, multiply by some 300 here. And I get, when I multiply these out, and my calculator's in degrees, I get this number. They don't tell us where to round. They just come on down here and say, oh yeah, that's about 120 feet. Remember to keep the units. I will be grading on the test for the units. This is 8.1. It's not on next week's test. It'll be on test number 3. So the problem at the bottom of the page is finding the height of a statue, which is way up on top of a building. And here's the drawing. Thank goodness they gave us a drawing. And so here's the little statue way up there at the top. And so what they're asking us to do is to find an angle all the way to the top of the little statue. And I find it again, the second angle at the bottom of the little statue. And it's not that we're finding it. Sorry about that. They've given us an angle to the top, and they've given us an angle to the bottom. I'm going to leave this one for you to do, because you're going to find the height from the bottom of the skyscraper to the bottom of the statue. That'll be this first one. That'll get us from bottom to bottom. And this other one is going to get you from the bottom to the top of the statue and its height. You need to practice trying to figure out how to calculate those and not looking. And then you're going to subtract the heights, and you'll get the height of the actual statue. I'm going to leave that one for you to do. And then I'm going to move on to example 10. So looking at example 10, this one's very detailed. You'll have a lot of information coming out of this problem. So plan to hit pause maybe multiple times, but the problem says that this lighthouse was in operation since 1846. It's called the Gibbs Hill Lighthouse. It stands 114 feet high on a hill that the hill is 240 feet high, so the beam of its light is 362 feet above sea level. There's a brochure that says this light can be seen on the horizon about 26 miles in the distance. Verify the accuracy of this statement. We're going to go through a couple of processes and come back to, did we get 26 on our calculations? And we're going to actually do 2 calculations to compare to see if the brochure was accurate, or if the brochure maybe stretched the truth a little bit, or could have said a real number that it wasn't. And so the drawing over here, and I've covered up part of my work just to be able to take this one step at a time. When you're looking at the drawing, we're going to incorporate the radius of the Earth. So the radius from the center of the Earth to the surface of the Earth is 3,960 miles. The Earth is curved. And you see the bottom of not the lighthouse, but the bottom of the hill, which goes up to here, which goes up to the lighthouse, and this is your 362 feet, because the hill and the lighthouse together form that total height from the Earth's surface. Also, since this is the curve of the Earth, and this is still the center of the Earth, we need to incorporate that this is going to be the distance of the side, or the length of the side of this triangle, which goes all the way with the 3960 plus this 362, but there's a problem. One's in miles and one is in feet. They are asking us, you can be seeing the horizon, it's talking about all of the distance and how far and all what's going on. It would be good if we had an angle somewhere. So let's pick on this angle for now. Let's pick on this angle and notice what we do have. From this angle, we have an adjacent, and if we put all of this stuff together, we have a hypotenuse. So that's where we're going to start. Adjacent and hypotenuse, it's sine. Sorry, it's cosine. And so when I uncover this piece of paper, we're going to see something going on with cosine, this part of the Earth's radius, and then trying to get these two together. So if you look with me right here, here's our cosine. I've got a split on my screen. I'll fix that later. And so looking here at cosine, that's the radius over here for adjacent. And then down here in the denominator, we've got to take our 3,960 miles, add it to our 362 feet. But first we have to convert it to miles by dividing it. Here's the equivalent. 1 mile is 5,280 feet. So you, at this point, should probably stop the video and make sure that you can punch in this 3960 divided by all of this, and do you really get that number? Because once we have that number, we really don't want that number. We need to know what is theta, which means we're going to have to do inverse cosine of that number. And so if we move down here, and I'm even going to do another sticky note. Just too much going on. I'm trying to keep it simple. So I'm going to cover that up, and I'm going to cover that up. So that once you type into your calculator the inverse cosine of this 0.999, everything we got up here, we're able to get this number here, degrees. Pause, make sure all of that is good, and you're ready to go to the next part, because remember the original question was, the brochure said 26 miles. And we're about to find out, is that right or is it not right? And we're going to go at it a couple of ways. However you're doing vocabulary, you need to pay attention right now with your sticky notes or index cards or highlighters or something, because here comes a definition. It says the brochure does not indicate if this is talking about nautical miles or statute miles. So let us calculate both. We're going to start at this next paragraph sentence. The distance called nautical miles, and there is a problem in our book, is the measure, and this is where I would start underlining. Nautical miles, measure of, the angle, but it's the angle in minutes. And you'll have to go back to when we first got together this semester, when we were converting degrees and minutes and all of this information. And now I'll uncover this top part. If I go back to this 0.33715 and multiply it times 60, I get it to minutes. And so we now have an answer of 20.23 minutes. And then head back down here. That means, since it's now in minutes, that this was 20-something nautical miles. If you want to go ahead and look back up here, they said, you can see 26 miles. Well, in this case, you really can only see 20 nautical miles. So that brochure is stretching it on nautical miles. But wait, there's more. There is also the distance in statute miles. So I would highlight and underline. If I ask you on a test, how can you find statute miles? Nautical miles, you're going to take your degrees and multiply by 60. Bingo, done, I'm there. Statute miles, I need to remember, oh wait, I already know that formula. But I have to underline, remind myself that that theta's got to be in thadians. Nice. That theta's got to be in radians. And so they go back up here. Where are we? Right? Let me get my little sticky notes going again. They go back up here to our degrees, the 0.33715. And here we are down here that our theta is 0.33715, and they say, oh, poof, it's a radian. I thought I'd go ahead and show you that we take that, and let's get the book up, and we multiply that times our pi over 180, which is stuff we did together a long time ago. And we do that, we get this many radians. But the formula is to take your theta in radians and multiply it by the radius. And the radius in this case happens to be, let me adjust here a little bit. The radius happens to, oh, come on. I know we can show it. The radius happens to be 3,960 miles, which is back over here for the radius of the Earth. And when I multiply these two together, go to the top of the next page with me. Leave those there. We're at the top of 529. And at the top of 529 is where it says, voila. We calculated nautical miles on the other page, and then we started and are calculating statute miles. So in statute miles, it says it's 23 miles that we can see. Bottom line, in either case, the brochure was a little bit stretching it. It overstated the distance of how far you could see on Gibbs Hill Lighthouse. We're through this problem. You might want to go back and hear it again, play around with it again, but we're moving on. Moving on to one more concept. And so the one more concept is in navigation and surveying. In navigation and in surveying, there's a thing called direction or bearing from a point O to a point P. It's going to be an acute angle, it's a ray, it's a vertical line. I need you to highlight north-south. We're going to base everything we're about to do off of the north-south line. And if you look at this drawing here, you will see that there is a north-south. I see west-east. I don't care right now. North-south is the line I'm looking at. And we're going to base what we're about to do on the north-south line. So it says in figure 16, we've got some illustrations. Notice we're going to look first from O to P1. So I'm going to cover up O to P1, and I want us to first notice, are we in the northern half or the southern half? And you'll note that we're in the northern half, and that's what you start by saying. I'm in the northern half. So your first part of this answer is either N or S. We are in. Then you're going to state the degrees coming off of that vertical north or south. We're coming off of it by 30 degrees. And then which way did you go? Did you go to the east side or did you go to the west side? And we went to the east side, and you're done. You just labeled the direction, or what's called the bearing. And so now it says in this figure, what is the bearing from O to P4? And so to find the bearing from O to P4, I'm going to cover all of this back up, and I'm going to ask 3 questions. Are we in the north part or the south part? And we are in, right here, we are in the south part. What are the degrees coming off of the vertical? Not off of the horizontal, off of the vertical. And we're coming off of that by 20 degrees. And when we came off of the vertical, did we go to the west side or the east side? And we went to the east side. And that concludes how to find bearing. That's all the video I'm making for this 8.1. Back in your notes, in your assignment, you're going to see that there's another video for you to watch. And then you'll end up doing example 12. Great job. Hang in there. But this concludes the middle portion of section 8.1 in our trade class.